Last video we talked about the sort of qualitative background mostly to what's going on inside an electrochemical cell. We talked about the electrochemistry, we talked about the potentials and electric fields that exist inside, we talked about the roles played by the screening layers on each electrode. Now let's talk about the actual thermodynamics. Of course, core to anything in thermodynamics is work and free energy and energy generally. And to do that, we're going to understand that, we're going to look a little bit more closely at the cell potential and its relationship to the free energy of reaction. So to do that, let's consider a thought experiment in which I start with a two half cell like this one up here. I'm going to consider, in fact, this exact cell. Actually, let me copy it down so we can sort of look at it. And let's see if I can find some space for it. I guess I'll have to create some space here. I'll create it up here. Yeah. There, now we can look at our cell as we're talking about it. That's a little easier. All right. So we're going to start by applying a small voltage up here. And just like a millivolt or something, and that's going to cause, we're going to start out with everything at equilibrium, so the concentrations in both sides are adjusted so that this overall chemical reaction would be at equilibrium if I don't apply any voltage. That means that when I start applying the voltage here, I'm disturbing an equilibrium situation. There can't be any cell-generated voltage when I do that. So I'm going to start disturbing my equilibrium situation. I'm going to transfer a few electrons. I'm going to create a few zinc plus ions on this side and reduce a few iron 2 plus ions on this side into iron. But after I do that for just a little while, the whole system will come back to equilibrium and I'll be back to a situation where the voltage that I'm applying here is exactly balanced by a reverse voltage that's now generated by the reaction itself to balance the small voltage that I applied. Now I continue turning up the voltage higher and higher, and as I do, I create more products on this side and I create more products on that side. I deplete more reactants on both sides. And I basically continue applying voltage until I get to the state that I want, until I get as many products on in both pots as I want and deplete as much reactants in both pots as I want. And at that point, I'll have some finite voltage that I've applied, some voltage V, but I'll also have a reverse voltage, which is called E, the electromotive force, that represents the back resistance of the cell to the changes I imposed with my applied voltage. The fact that I applied it slowly and that at every point there was a backwards voltage that was opposing me means that that's a reversible process. At every point as electrons were being transferred, work was being done by the voltage that I was applying, and that's reversible work. Therefore, what I'm doing is changing the free energy of my system, or changing the free energy of reaction. And so now, if I swap the power supply for a voltmeter, keeping everything else constant as I do so, what am I going to read? Well, I'm going to read a voltage on my voltmeter that's equal to the negative of the voltage that I was originally applying. And that is called E. It's called the potential generated by the reaction. It's called the electromotive force. Somewhere I've got electromotive force written, but let me write it out here. It's not really a force. Electromotive force is an unfortunate term, but that is what it's called by convention anyway. It's really a potential. It should be called the electromotive potential, I guess. And it's the same thing as what we applied, but it's the potential generated by the reaction itself instead of by the power supply. All right. Since it's reversible work, since that electromotive force represents reversible work, it must be a free energy. It has to be the free energy of the full reaction. We only transferred electrons through the wire. We didn't transfer the ions through the wire. But the ions were being created or destroyed at the same rate as the electrons were moving through the wire. And the amount of work done to move those electrons has to be the same as the amount of work that was necessary to create all those other species at the same time. And so the work that we're doing, the reversible work that we're doing, is the same thing as the free energy for the overall reaction in both half cells going at once. That has to be related to the potential. The potential is energy, free energy we see now, per unit charge. So all we have to do in order to get what the free energy is multiply this potential by however much charge was transferred through the wire. The amount of charge transferred through the wire is the number of moles of electrons transferred through the wire. That's what that N value is, the number of moles of transferred electrons. Times the Faraday constant, right, which is the number of coulombs per mole of electrons. So this whole quantity is nothing but the number of coulombs transferred. It's the charge that was transferred. Remember, the Faraday constant is 96,485 coulombs per mole of electrons transferred. So it has a value that we know. We multiply that by whatever voltage prevails at the end of our experiment, our thought experiment, and that gives us an energy, and that energy we've seen has to be the free energy of reaction. Just as an aside, electrical units are not familiar for most chemists, so the coulomb is the standard SI unit of electrical charge. 1 coulomb times 1 volt, which is the standard units of electrical potential, is equal to 1 joule. So volts times coulombs is joules. Okay, we know already that the free energy for any chemical reaction has to be equal to the free energy at standard state plus RT log of the Q for the reaction. There's a Q for this for any redox reaction, just like there is for any reaction. And now we know that delta G for the reaction, this is for reaction in both cases, is equal to minus NF times the cell-generated potential, and therefore the potential is equal to delta G of reaction divided by minus NF. So if we divide both sides of that by minus NF, we should get an equation for the cell potential, and here it is. E is equal to plus E0 minus RT over NF log of Q, and that's the Nernst equation. This is the cell potential. This is the cell potential at standard conditions. N is the number of electrons transferred during the overall chemical reaction, the number of moles of electrons transferred. And RT is, of course, just the gas constant times temperature as usual. So here's the Nernst equation over here in the regular notes. And we can now use that Nernst equation to predict the cell potential that will exist for a given chemical reaction under a given set of concentration conditions and at a given temperature. Notice that the Nernst equation says that the cell potential depends on Q for the reaction, and remember that the Q for the reaction depends on activities or concentrations for the reactants and products of the overall reaction. So that says that the cell potential depends on concentration. You can't know the cell potential just by knowing what reaction is taking place. You have to also know what the concentrations of reactants and products are in order to calculate and predict the cell potential. You also have to know the standard cell potential. We'll talk about that next. So standard reduction potentials are values that are tabulated. They're in tables. There's a table in the back of Engel and Reed that you can look up standard reduction potentials as you like. They apply to each half cell independently. So there's an oxidation half cell in every electrochemical cell. There's a reduction half cell in every electrochemical cell. In the oxidation half cell, there's an oxidation reaction taking place. Of course, in the reduction half cell, there's a reduction reaction taking place. But the tables only list reduction potentials, which means that in order to use the tables, you have to reverse this oxidation reaction into and write it as if it were a reduction. And then you can look up the value in the table, and you can also look up the value for that reaction, for the reaction that's happening on the reduction side. And then because you reversed the direction on the oxidation side, you don't add these two guys together. You subtract them. You subtract the reduction value from the oxidation value. That minus sign is accounting for the fact that we were really doing an oxidation on the one side. All right, let's do an example of using all this stuff. So I've written a electrochemical cell here with a chromium electrode, a tin electrode, chromium ions, chromium 3+ ions in solution, but at low concentration, and tin ions in the other half cell, also in solution, but at high concentration. So I've set up a cell that's not at standard conditions. That means the cell voltage is not going to be the standard state cell voltage. And we want to do a bunch of calculations with this to see, first of all, what the real cell voltage would be, and a number of other things we can easily calculate from this. Note that I've set things up at 298 K, so or at least at the standard room temperature sort of conditions. I don't know at the beginning which side will carry out oxidation and which side will carry out reduction. I just guessed. One side has to be oxidation, one side has to be reduction. I guessed that it would be the chromium side that's oxidized and the tin side that would be reduced. If I'm wrong about that, then at the end of all this, I will calculate an overall cell potential that's negative. And in that case, I'll know that I chose wrong, and I can just reverse everything. So it doesn't really matter. As long as you make a reasonable choice and follow it through all the way to the end, you'll either get a positive cell potential, in which case you were right, or you'll get a negative cell potential, in which case you were wrong, and then you can reverse everything at the end. All right, so let's go through the calculation. First of all, in order to use the Nernst equation, ultimately I'm going to want to use the Nernst equation, right? I'm going to want to say that the cell potential is equal to the standard state cell potential minus RT over NF log of Q. In order to use the Nernst equation, I'm going to need the standard state cell potential. I'm going to need to know how many moles of electrons were transferred. So how many moles of electrons were transferred over here? It might look like it's 3, right, if you look at this side. It might look like it's 2, though, if you look at that side. How many moles were actually transferred? We're going to have to balance the reaction to get that number. So this number of electrons transferred always requires that you balance the reaction. Then we know the temperature. We're also going to have to balance the reaction in order to calculate Q, right? We need to know stoichiometric coefficients for reactants and products in order to calculate Q. So balancing is going to be an important part. All right, so assuming that things are as I have set them up, oxidation on the chromium side, reduction on the tin side, I look in the standard tables for the reaction, for the reduction reaction for the chromium side, which would be Cr3 plus 3E minus goes to Cr. And from the tables, the value I see for that is minus 0.774 volts. In other words, the value I've written down over here is the value as it actually is in the tables for a reduction. I haven't changed it, and I haven't changed that sign. The minus sign was there in the tables. Likewise, for the tin side, I read minus 0.1375. Those are both the table values. Now when I go to calculate the overall cell potential, I just take the reduction number and I subtract the oxidation number, where that minus sign between the two is because I'm implicitly reversing the oxidation number, right? I'm putting a minus sign in front of the oxidation number. All right. And that gives me a value of 0.6065 for the standard state cell potential. Now, this is a positive value. The standard state cell potential, let me blow that up a little bit, is related to the standard Gibbs free energy change for the reaction with a minus sign in between. So a positive cell potential means that the standard state means we're going to have a negative standard Gibbs free energy change for the reaction. That's going to make the equilibrium constant for the overall reaction greater than 1, and that means we've got a product favored reaction. You can tell all of that just by looking at the sign of the standard state cell potential. All right. The next thing we have to do in order to get our N value over here, and in order to get Q, is we've got to balance the reaction. In order to balance the reaction, the overall net electrons, the number of electrons produced by the oxidation side and the number of electrons consumed on the reduction side have to cancel. You got to produce exactly as many electrons as you consume on both sides. You produce 3 electrons per mole of chromium on the chromium side. You only consume 2 electrons per mole of tin on the tin side, which means that I have to adjust things. I've got to multiply this reaction by 2, and I've got to multiply the tin reaction by 3, so that I get 6 electrons produced and 6 electrons consumed on both sides. If I add these two guys together, you can see that I'm going to get 6 electrons produced and also, 6 electrons consumed and 6 electrons produced. That means that my stoichiometric coefficients for chromium and tin aren't 1s. They're 2 for chromium and 3 for tin. All right, but that means that my N value here that I need for the Nernst equation is 6. Next, I need Q, And now that I balance the reaction, I know that Q is going to be equal to, so here's my overall, well, let me write it all out. My overall balanced reaction is then 2 chromiums plus 3 tin 2 pluses goes to 2 chromium 3 pluses plus 2 tins. And that means that my Q is going to be the activity for the chromium squared divided by my activity for the tin cubed. And next I have to turn these activities into, I have to relate them to concentrations. So I'm doing that over here. The activity, so here's my Q. The activity for the tin is the activity coefficient times the concentration. The activity for the chromium is the activity coefficient times the concentration. And that means I've got to calculate these activity coefficients. The activity coefficient, assuming an activity coefficient of 1 on the chromium side, might be okay, because I've only got a 1 millimolar chromium solution on that side. That's pretty small. Maybe assuming the activity coefficient on that side is 1 would be okay. But I've got a 1 molar solution of tin chloride on the other side. This activity coefficient is not going to be close to 1. So I really need to do a calculation at this point to get these activities close to right. So now we have to calculate activity coefficients. I'm going to use the Davies equation. I'm going to use the Davies equation because I've got such a high concentration of tin over here. I could use Debye-Huckel. I could use extended Debye-Huckel. Debye-Huckel probably isn't very good at 1 molar. In fact, it's probably lousy at 1 molar. Extended Debye-Huckel is probably also not so great at 1 molar. This is really a high concentration. We're really in the range where we need the Davies equation, which is best for these high concentrations. To use the Davies equation, here's the Davies equation down here. I need the ionic strength. For a chromium solution, I'm going to get Cr3 plus 3 chloride minuses when the chromium chloride dissolves. And so working through the usual stuff for an ionic strength, that gives me 6 times the nominal chromium chloride concentration of 1 millimolar. And so my ionic strength is 6 millimolar. And that's what goes in here for the Davies equation. If I plug that in and do the arithmetic, I get an activity coefficient on the chromium side of 0.92. Notice, by the way, and I think I didn't point this out before, but let me point it out now, that the gamma plus minus for the chromium is not the same as the gamma plus minus for the tin, because they're in 2 different pots. Up to now, in all the examples that we've done, these gamma plus minuses have applied to a solution, only one solution, but we really have 2 different solutions here. So there's 2 different gamma plus minuses. We've got to do 2 different calculations. So that's gamma plus minus for the chromium side. Doing the same stuff on the tin side, we get that the ionic strength is 3 times the nominal tin concentration, the tin chloride concentration. The tin chloride concentration is 1 molar, which means that the ionic strength is 3 molar, and therefore a 3 goes in here in the Davies equation and also there. And if you do all of that arithmetic, you get an activity coefficient of 1.37. Notice that that's an activity coefficient that's bigger than 1. The ionic strength is so high in this case that the Davies equation is predicting, now I don't know how accurate the Davies equation is, but it's predicting that the effective concentration of calcium chloride, of tin chloride, is actually greater than the nominal concentration. Usually it's less, right, because ions pair up. But when the concentration gets high enough, repulsions between the ions is big enough to actually make the effective concentration bigger than the true concentration, and that's happening in this case. All right, so now we can calculate the actual activities. We have the activity coefficients. we get a little less than a millimolar for the chromium activity. We get a little greater than 1 molar for the tin activity. We plug that into our expression for Q, do the arithmetic, and we get a Q value of 3.3 times 10 to the minus 7. Notice that it's quite a small value, and that reflects the fact that we have not very many products, which is the chromium 3 plus here, and we have a lot of reactants, which is the tin 2 plus. And that's going to mean what? We can predict right away that when Q is less than 1 like this, and we plug a value that's less than 1 into the Nernst equation, this quantity is going to be negative. The minus sign means that this whole end term is going to be positive, and that means we're going to get an overall cell voltage that's greater than the standard state cell voltage. So if we plug the numbers in, there's our Q value, there's our N of 6, RT is 2479 at 298, there's the F value of about 100,000, again doing the arithmetic, and we get a small positive, relatively small positive value for this whole end of the Nernst equation, and therefore indeed our predicted cell voltage, our actual cell voltage at non-standard conditions, is a little bit greater than the standard state cell voltage. All right. I say all those things that I just said here, that anytime you get, you're starting off your reaction under conditions where there are few products and lots of reactants, then you can expect a cell voltage that's a little bit bigger than the standard cell voltage. Okay, that's our example. But we can do a few more other things with this example. That's the main part of the example. Anyway, we can do a few more things. One thing we can do is calculate what this equilibrium constant is for the overall cell reaction, right? There's no equilibrium constant for a half reaction, but there is an equilibrium constant for the overall cell reaction. The equilibrium constant is related to the standard cell voltage, as I set up above. And so delta G is equal to minus NF standard cell voltage E. We calculated that down before. We're multiplying that standard cell voltage by 100,000. So it is a generally true thing that relatively modest cell voltages, so this is only 0.6 of a volt, it's not a great big cell voltage, gets multiplied by 100,000 and then gets multiplied by 6 because our N value is 6, gives you a great big delta G, standard state delta G value for this reaction. So modest positive cell voltages usually correspond to really high favorable delta G values for the same reaction. In this case, notice the minus sign here means that it's a negative delta G, as I said above, of minus 351 kilojoules per mole. That's a big cell voltage, or that's a big reaction free energy. Now we can plug that into our formula for the equilibrium constant, and we expect a big equilibrium constant since we've got a big delta G, and indeed we get one, 3.2 times 10 to the 61. So it's a very product-favored reaction, as you would expect. And I'm just saying all those same things down here. You can read those in the notes when you look at it offline. Yes, and this is another point that's worth making. In the present case, we measured the E0 value and got the K value. It's also possible to measure the K value in other ways by measuring concentrations in solution at equilibrium, for example, and predict what the standard state cell voltage will be. So you can go both ways. All right, there's one more thing topic we should bring up. It comes up at the end of Engel and Reed, and that's the fact that by making measurements on the standard cell voltage as a function of temperature, we can then use this relationship to get not just the standard Gibbs free energy change of reaction, but also the delta S of reaction, and then using both of those, we can get the delta H of reaction as well. So we can get a pretty complete characterization of all the thermodynamics of a reaction pretty easily just by looking at the readings on a voltmeter as we heat up our reaction a little bit. So here's the relationship. Here's the general relationship, right? The entropy is equal to minus the Gibbs free, the derivative of the Gibbs free energy with respect to temperature at constant pressure and mole numbers. Applying that to a chemical reaction, we get that the delta S of reaction is the derivative of the standard state Gibbs free energy of reaction. And if I plug in delta G equals minus NFE here, then I get that the delta S of reaction is related to the temperature derivative of the cell potential. In other words, if I set things up like this, start measuring the cell potential on my voltmeter and warming up the reaction as I do that, then I can plot the cell voltage that I read as a function of temperature. That should be a straight line, or roughly a straight line at least. The slope of that straight line will be proportional to, by NF, to the standard entropy of reaction. Once I have the entropy of reaction, then I can use the fact that delta G, which I can also measure at any one temperature, is equal to delta H minus T delta S. I now know this, I know that, I can solve for that. And if I do that and convert everything, put everything in terms of cell voltages rather than delta G's, then I get that the delta H of reaction is NF times minus the cell potential plus T times the slope of the cell potential as I change the temperature. And I didn't plug any numbers into that, but that's in principle something that you can do. And that reflects actually the reason that electrochemistry is a very popular topic among chemists. It's very powerful. You can get a very easily, and with relatively easy measurements, you can get, you can do these measurements in your kitchen, right? You can get a pretty fair characterization of a complicated chemical reaction. With that, we'll stop. The next topic I'm going to bring up is a big switch. We're going to switch from now the applications of thermodynamics to the beginnings of statistical mechanics. So we'll take up that large and very important topic next time.